So when we graph the family of solutions, we're going to get a whole series of solutions that kind of follow this kind of shape. Okay, and if this differential equation is going to give us the slopes to all those pieces. Okay, so I can actually use this differential equation to generate a bunch of slope pieces like I did here. dy by dx equals negative 4xy squared. So I can choose a point at 1, 1. Sorry, x is 0, y is 1. And I plug it into there, I get a slope of 0. Okay, so, and that's true there. Okay, if I choose a point at, 1, x is 1, y is 1, I'm going to get a slope of negative 4. Okay, so it's going to have a slope of negative 4 here. At negative 1, positive 1 here, I'm going to get a slope of positive 4, okay, through there. And what I can actually do is generate a whole bunch of these pieces of slope. And if I just draw on all these different points all across this whole graph, all these little slope segments, what ends up happening is you end up being able to see generally how the graphs, the family of solutions, should be looking, the shapes of those families of solutions. And this is something called a slope field. Okay, so I just did a couple here, but if I were to do a whole bunch of them, okay, you get a whole field that looks like this. So you have all these little slope segments that are calculated using the original differential equation. Because remember, the differential equation is the derivative, so calculate slope. So we can calculate these slope pieces here. Okay, and these are called slope fields. And if you take a look at the slope field, when you look at the field, you get a general idea what this shape of the graphs are going to look like. And here on the right hand side, we see all the different solutions, possible solutions, depending on where the graph goes through, okay? Depending on the initial condition, or the plus c. So this is very useful to get an idea of what the graph looks like when we get, especially when we get differential equations that cannot be solved. Okay, if we have a differential equation that cannot be solved, at least we get a look at an idea of what this graph's going to look like. And in fact, if we know an initial condition on the y function, what we can do is then take a point, let's say the initial condition is that point there, and we can use that point and we can actually just kind of start following the slope field and seeing that there's a graph that kind of looks like that. And let's say there's a point here on this graph. Well, it's pointing towards this, and it looks like it's kind of going up in this direction. It's kind of pointing down here, like that, okay? And if it went through that initial point, we get these different solutions. And these would represent the different plus c solutions. And we can actually, even though we can't actually solve this differential equation, if we have the derivative and we know where a point on the original y function is, we could potentially just follow this slope field, and at least we have an idea what this graph is going to look like. And that's what's going on here. These are actually solved differential equations, but even if we can't solve it, at the very least we start getting an idea of what the function is going to look like, or the shape of the function. Okay, but in general, the slope field will give us the solution to the family of solutions, all the possible plus c value solutions that we can get from solving that differential equation. And sometimes we can actually solve them and come up with the actual graph. Sometimes we just have the slope field and we just have to estimate what that function is going to look like based on following the slope field. So if we want to find that solution to a specific function like we did here, we just know, if we know the position and we can actually solve for the plus c, we can solve the differential equation and find the plus c, we can get the specific curve. But if we can't do that, we can at least trace out the curve based on using the slope segments. Okay, this is the idea behind slope fields.